What is up, everybody? It's Miss Wesley. It is calc time. I'm excited to be here with you today, working on the example starting on page 4 of your definite integrals packet. And today, I like to say it's a big day. Today is a huge day as we get to the fun. I see that at the top, emphasis on fundamental theorem of calculus, and I hope it's going to be fun. I see a couple fun-looking gentlemen at the top of the page. Don't know if you recognize them. They're just, no big deal. The fathers of calculus, Leibniz and Newton at the top here. And you might have heard of a fundamental theorem of a lot of other areas of mathematics before this. So we can talk about them. No need to really write them down, but think about arithmetic. It's pretty fundamental that every integer you can think of, any positive integer, can be written as a unique product of primes. Prime factorization is a pretty key feature to arithmetic operations. Fundamental theorem of algebra, this gets used all the time in pre-calc and other areas of mathematics too. Every polynomial of degree n, a fifth degree polynomial, has exactly n zeros or roots. They might not all be real, there might be repeats, but every single one has n of them. I couldn't find in my research a fundamental theorem of geometry, so I was thinking maybe there isn't one, maybe there's just a bunch of different fundamental theorems of certain areas of it, but Pythagorean theorem seems like a common thread with a lot of geometric ideas. And then I would throw this back to my students taking statistics to answer this question for me, or maybe talk to Mr. Russo and find out what is the fundamental theorem of statistics. Some people call statistics the most applicable and most important branch of mathematics because it has so much to do with everyday life. When I was looking stuff up, I saw maybe the law of large numbers, and that's that for a large repeated number of trials, the average observed value you have approaches the expected value for the outcome. And then central limit theorem, and for this one I'll have to look at what I wrote down. The mean of a sample of size n is approximately about a bell-shaped curve, about normally distributed when n is large. So all that, fundamental theorems of the other areas of mathematics. Now we get to do this for calculus. We have so far been introduced to two major branches of calc. Taking derivatives was called differential calculus. And that was all well and good. That was a lot of stuff we did in the beginning of the year. And now we've started talking about integral calculus, taking antiderivatives, and the past couple of days have related it to area under a curve. Well, today you're invited to a wedding. It's the wedding where differential calculus gets married to integral calculus, and we connect the two. Leibniz and Newton were the guys at the top, the ones to really discover this. And I'm telling you, if the only way to solve this problem of finding area under a curve was to do it how we've been doing the past couple of days, adding Riemann sums of areas of rectangles or trapezoids or anything else, this would be very cumbersome and there must be a shortcut. So today we get this fundamental theorem and we're going to be able to more easily compute these areas under the curves. So here's where I would write stuff down. Fundamental theorem of calculus. You have a function that's continuous, no skips or gaps, on a closed interval from A to B. We've seen this a little bit, this notation the past couple of days, a lower limit of integration and an upper limit of integration. If capital F is your antiderivative, you can actually solve this without having to add up a bunch of areas of rectangles. You can take the antiderivative, capital F, evaluate it at the upper limit, so find the antiderivative and plug in B, the number that sits up top, subtract what you get when you evaluate the antiderivative, capital F, at the lower limit, minus f of a. So antiderivative at B minus antiderivative at A. So the trumpets are sounding. This is a huge discovery. This is going to make a question like the one at the bottom of page 4 a lot quicker. And you might have remembered this was the warm-up question from the very first page of the packet. We had a curve, y equals x squared from 0 to 1, and we were trying to use rectangles to just estimate the area under this curve. If you recall, or if you flip a few pages back, we were getting overestimates around 0.4 something, we were getting underestimates around 0.2 or 0.3 something. Well, let's just cut to the chase. Let's apply the fundamental theorem, and here's the notation. It says first, take your antiderivative. I'll get rid of that. So take the antiderivative of x squared, and let's write it right next to it. It's going to be x to the third over 3. Usually plus c. Can you hold off on putting the plus c because this is definite? I'm going to draw just kind of like a nice long vertical line here. And I'm going to put the 0 down at the bottom and the 1 at the top. This is just notation that says in a second what we're about to do is we're about to plug in 1 and subtract what we get when we plug in 0. So we'll make it 1 cubed over 3. We're plugging in the upper limit of integration minus, because that's what the fundamental theorem says to do, this antiderivative evaluated at the lower limit, 0 cubed over 3. So your answer, and you might have guessed this, your exact answer for area under that curve is 1/3 minus 0/3. It is 1/3 of a unit squared. So we'll say squared units. 0.3 repeating was going to be the exact answer for that. Now, I don't know if any of this is throwing you off. I wonder if you're thinking, Miss Wesley, why does the plus C just get to go away in this packet and we don't have that constant of integration on our answer? There's a good reason for it. We can put a proof of it underneath. Sure, I could take this original and I could include the plus C. So integral from 0 to 1 of x squared taken with respect to x is going to be x to the third over 3, and let's include the plus C. Let's put plus C right next to it. Well, we still have to evaluate this because it's a definite integral, and I wrote this incorrectly. It should be from 0 to 1. How about? So from 0 to 1, I'll just draw the line and put 0 to 1. You would get 1/3 plus C minus 0/3 plus C, wouldn't you? And the C should cancel. It's 1/3 plus C minus 0 minus C. Every single time you take a definite integral, the C's are going to cancel. And as long as you see those little numbers, the limits of integration on top and bottom, there's no need to include it in the answer. Moving along to page 5, this is just a good reference space to take a bunch of notes about what you can and can't do with definite integrals. And what's cool is this first guideline here. It's nice to know that as long as we can take an integral of a function, and unfortunately there are some functions that we don't have integration rules for just quite yet, but as long as we can take an antiderivative, there is a shortcut to finding the area under the curve. Thank goodness we won't have to be, like we've been doing the past couple of days, adding up Riemann sums and calculating the sum of a bunch of areas of rectangles or trapezoids or whatever the case may be. Let's look at number 2. It says, use the notation, same notation we used on the last page. When applying fundamental theorem, this notation is convenient. We're going to call capital F the antiderivative of little f of x. So capital F of x, the antiderivative, evaluated, so we'll use the vertical line from A to B, equals the antiderivative evaluated at B minus the antiderivative evaluated at A. So we kind of just recopied fundamental theorem there. Let's try it with a function that's 1 power higher than the one on the last page. Can you integrate x to the third? Let's find the antiderivative. So go up a power, x to the fourth over 4. We won't write a plus C because this is a definite, not an indefinite integral, and I instead want to evaluate this from 1 to 3. So fundamental theorem says plug in the top number first, the upper limit. So 3 to the fourth over 4 minus 1 to the fourth over 4. And this gives you 81 fourths minus 1 fourth. So you get 80 over 4, which is 20 square units. I want to relate this answer to what we've been talking about the past couple of days. If you were to just sketch the graph of y equals x to the third, rough sketch of that S-curve, what we just found, and that's x to the third, what we just found is that from x equals 1 to x equals 3, the area, this little shaded region in here between the curve and the x-axis, is actually 20 square units of area. And we didn't need a rectangle, we didn't need a Riemann sum or a limit to find that. And we've actually already gone over the third guideline that you don't need a plus C when it's a definite integral. Really, you'd have the antiderivative evaluated at the upper limit of integration plus a C, but then you're subtracting it evaluated at the lower limit plus a C as well. C's are always going to cancel, and you have what you wrote up here. Nice guidelines to try these problems by. I actually want to jump right to an application because I think we know enough to be able to solve a problem like this. So that's kind of cool. You have a parcel of land that's 100 feet wide and bounded, let me move myself down, bounded by streets on 3 sides and a stream on the 4th. So you have street, 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 and a curved stream, and somebody was cool enough to put this on a coordinate plane. And we have a model of the stream being x cubed plus 1. We have our setup here, and we can see the area graphed, and the land is appraised at $12 per square foot. I want to know how much is the land worth. We need calculus to get us the area of the shaded region, and then we can multiply it by the price to get the value. So let's first get the area. I'll say area equals integral from, well, this is kind of cool. Let's set it up based off of the picture. Use x values. So go from 0 to 1 of the curve that's bounding the area from the top. So it'll be of x cubed plus 1, taken with respect to x. You can tag a dx on the end of that. Go ahead and use the fundamental theorem. It says take an antiderivative. So we'll take antiderivative of this, x to the 4th over 4. and then plus, what's the antiderivative of 1? So something that has a derivative of 1 would just be x, right, when you have a constant there. Instead of a plus c, let's evaluate this from 0 to 1, and no plus c needed. Well, 1 goes in first. 1 to the 4th over 4 plus 1, and minus what you get when you plug in 0, 0 to the 4th over 4 plus 0, that's going to be minus nothing. And you just get 1/4 plus 1, and the area is 1.25. Let's put units on that. X is measured and Y is measured in hundreds of feet. So this is 1.25 hundred square feet. And there's a little bit that's tricky because we're talking about area here when you talk units. That's technically, if you wanted to get a number for it, it's 1.25 times 100 square feet, so times 100 feet, times another 100 feet. So technically, without getting too deep into it, if you're talking about square feet, it's 12500, 12,500 feet squared is going to be the value that we use for the area. If you take this and multiply it by the price per square foot, multiply it by 12, you'll get the value of the land. So we can finish the question. And it is valuable, $150,000 for that parcel of land for the value. A few more rules at the bottom, a little bit more to copy if you don't mind. Constant, multiple, and sum difference rule. I'll put these guys in parentheses because they're very common sense. I'm going to enjoy talking about 3, 4, and 5 a little bit more. But just a quick recopy of this rule for number 1. Constant multiple outside of an integral, not a big deal. You can actually just leave it in your answer and you have the liberty to slide it inside or outside of the definite integral. You can make this k times the integral of f of x taken with respect to x. So that k can slide inside or outside if it's a constant of the integral sign. You also can take definite integrals of separate functions, separate parts of sums separately. So you can make this the integral from a to b of f of x taken with respect to x, separately plus or minus a whole nother definite integral from a to b of g of x dx. So just using the principles we used before, we always knew we could take derivatives, antiderivatives, term by term if need be. Here's a curious one. Rule 3. The integral, now there's no typo here, the integral from a to a of f of x equals 0. And I'm wondering if you could explain to me why. Why would the integral from a to a be 0? Well, let's think about it. Let's say I have a curve, any old random curve. I'll just draw a line there. I want the integral from a to a. There is no area here. If the number is ever the same on top and bottom, you're talking about no area below the curve. So you won't really see this too often. If you ever flip-flop these numbers, you actually get the opposite sign of your answer. So there's a rule that we should put here. The integral from a to b of f of x dx, if you switched the limits of integration and put the b down here and the a up there, you'd get the same answer. It would just be the opposite sign. So it equals negative the integral from b to a of f of x dx. Again, this rule comes more into play a little bit later down the road. There's also a subdivision rule, and I put a picture of it beneath. I think this is a good one too. If you wanted to split this whole entire area up into 2 easier to deal with parts, you could actually add the separate integrals. The whole integral from a to b equals the integral from a to maybe, how about we say c of f of x dx, plus separately the integral from c to b. You can actually just subdivide the area and solve this in 2 parts. More to come in the next part where we see these rules in action. Until then, signing off.